Well, I seem to have it.
Yes. So I think we can start. Welcome to everyone. This is a morning session, at least for me in Italy, in Europe. So thank you for being here. So we start this second block of the Education Teaching Modern Physics session of the Master Program meeting, and the first invited speaker is David Blair. So David, you are welcome, and you can start your presentation. Thank you.
Good. Thank you very much. Oh, what has happened? My slides are. Hopefully, this isn't going to automatically go forwards. So I wanted to talk about why it is so important that we should be modernizing school science, and why it's important that we be doing this from the very youngest ages of students. The particular importance is that there are declining attitudes to science, especially in developed countries. And reversing this decline is critical to our future, when we have to have all sorts of scientific and technical innovations to face climate change and things of that sort. And I believe that that this is an international problem, and it's got political and societal implications. And the most important thing is that if we teach obsolete science, 19th century science, during the compulsory years of school, then the majority are left ignorant and negative towards science. In Australia, science is compulsory until the 10th year of school. That's about the age of 15. So after that, most students don't go on with science. And so the majority of the population get all of their science learning up to the age of 15. So if all of that science learning, or the large majority of that, is 19th century science, they are left ignorant and negative towards science. And the negativity towards science we can see in the world as with anti-vaccine, anti-5G, anti-climate change, and alternative facts. They're all a result of ignorance about science, a failure to understand the power and importance of science. And so our project is aiming to reverse this decline by replacing implicit 19th century concepts with explicit 20th century concepts, starting at primary school, because that's where the implicit 19th century concepts are introduced and where they are cemented into people's minds. I'll just give you a little background for how the Einstein First Project arose. I've spent most of my career working on the detection of gravitational waves, but in all of that time, I've been involved with public education and schools education, and I kept experiencing the response from people in the public who would say to you, "Oh, you must be a genius to understand, Einsteinian physics, general relativity, and and atomic physics. Quantum physics, basically all of modern physics." In the year 2000, I helped to create this place, the Gravity Discovery Center, which you can see in the picture, with our Leaning Tower of Gingin, which leans a little bit more than the Leaning Tower of Pisa and is about the same height, and cosmology gallery, and an archway entrance, which is an 8-meter laser interferometer turned on its edge to be now used as the entrance archway. But when I did this, I naively thought that things like school excursions would lead to a spontaneous change in the curriculum. And that was really very naive. And at that time, I didn't understand how conservative curriculum authorities were and how difficult it was to change the curriculum. So in 2011 and 2012, we started some classroom interventions with year 6 children. We called this curved space and quantum weirdness. And the first thing that I found astonishing was that children were not astonished. They just took it in their stride. But at that time, an important member of our Einstein First team, Grady Venville, who is now Deputy Vice Chancellor at Australian National University, she said, "This is really interesting, let's research it." She was an education researcher. And so that was the beginning of our Einstein First collaboration, when we actually started to research the ability of children to understand these things. And then we've done many things over the years after that. We got funding for it. And in 2015, then we were approached by Magdalena Kirsting, who many of you know, in Oslo. And she contacted us and said, let's collaborate. And that seemed like a great idea. And there have been lots of outcomes of that, including this workshop that we are in right now. And now in 2021, we're going to be hearing about a new program just beginning in India. Ritik and Soumya, I think, are going to be talking live if the technology works. And we're in now the second year of testing of a full year 3 to 10 curriculum for schools. Sean is going to be talking about aspects of that, and Kyla's giving a talk about about a retrospective study where we tracked down the students from 2011 and 2012 to ask them what they remembered, and it's that paper has just been published by Physics Education. So that's the background. And so the particular important thing is that the idea of teaching Einstein First sounds like impossible nonsense to teachers who are imbued with a 19th century sort of Newtonian holist worldview, which is what almost all primary school teachers have. It's difficult for adults because they have to throw out assumptions that they learnt at primary school, but it's easy for kids because their worldview is not yet frozen. It's simple and intuitive, and it's perfectly suited, the subject matter is perfectly suited to using toys and models which they love and relate to. So our biggest challenge has been to make it easy for teachers, and that has taken a lot of thinking and understanding to see how we can teach teachers. If you say to a teacher, like in our first intervention, where it was called curved space and quantum weirdness, well, you say curved space to a primary school teacher, and they will be, their brains freeze up. What a weird idea, can't understand it. And so we have to find ways of overcoming that problem. Over the years, as many people know, when people try to do something like something different, you get problems and you get critics, and we've had lots of critics of our program. The first criticism has often been from physicists: you can't understand modern physics until you've learned classical physics, and that Newtonian physics is useful, you can't leave it out, and it's too difficult for children. And it's not important because it has no effect on our daily lives. And it's too difficult for teachers. Well, I just want to then show you our responses to these. First of all, our team has now proven without doubt, I think, that that first statement is not true. As far as Newtonian physics is concerned, we don't leave it out. It follows naturally. It's too difficult for children. Well, it's actually easier because it's got much more explanatory power. There's more explanatory power in the membrane analogy for curved space than there is in the idea of a force that mysteriously comes out of planets. And they say it's not important. Well, you can make a huge list of things where the Einsteinian understanding is important. GPS navigators, which have to correct for time dilation, gold, where the electrons are relativistic, partial reflections that can only be explained by a sort of probabilistic understanding of quanta, radioactivity, that's also all probabilistic, climate change, which involves quantum interactions in the atmosphere of photons and molecules, solar panels that rely on the photoelectric effect that Einstein won the Nobel Prize for. Phones, cameras, skin cancer, medical imaging, all those things are full of all of this physics. So all the relevant stuff in the world today is what we ought to be able to leave children who don't go on and specialize and become physicists. They should still be able to know something about all those things that are in that last yellow highlighted line there. But the difficulty for teachers is the important point, and we'd have to make that easy. So I'll be getting to that. So currently, what we do is we have these two conflicting paradigms. So the first 8 to 10 years of schooling, you learn about heat without mention of atoms. You think of heat as a calorific fluid or something, or you don't think what it is at all. You just talk about it without explaining what it is. Space and time are implicitly rigid. There's no discussion ever that space is able to be stretched and things like that. And we have a clockwork mechanical universe. And then for students who specialize, and maybe in the last year or two of middle school, a little bit of atomism comes in, the fact that the universe is made of fundamental building bricks, atoms, electrons and photons, and other things, of course. Space-time, we know, of course, as we heard from the Hildesheim group yesterday, only some states in Germany are teaching general relativity, so that the idea of this dynamic fabric of space-time, and otherwise you have to go on to tertiary to learn those things. And observations are defined by probability and uncertainty. Again, that is mainly in senior school. So we go from one paradigm to the other, and everybody has to switch paradigms, and that is clearly inefficient. So the logic behind Einstein First is that if we start with the modern paradigm, there's no relearning, everything is easier, and everyone learns modern concepts and language, and no one is excluded from the ideas that underpin the modern technological world. And I think if people can feel that they have some understanding of our modern technological world, they can be much happier with it. So in a nutshell, what we are advocating is early learning of the concepts and the vocabulary of modern science. So they learn fabric models of space-time, they learn about atoms and photons, and maybe as time goes on, they learn about subatomic particles and learn about the whole scale of the universe. And they need to learn unifying concepts, because physics makes things very, very difficult by defining all sorts of things under different technical names. And for example, fission and fusion that most people think are something to do with nuclear physics. Well, fission and fusion is about almost every process that happens in the universe. And related to that is the idea of binding energy. So you can talk about the fission and fusion of cells, of DNA, of nuclei, and there behind it all is one idea that there about the and that relates to the binding energy. Wave-particle duality is a very general concept that we introduced right from the very earliest ages, from the youngest children we worked with, year 3. And then maths is also important. And maths at primary school is normally about arithmetic. It's about learning your tables and things like that. But what is really far more important today is to have a deep understanding of powers of 10. A deep understanding of the use of vectors, which we call for children, the maths of arrows, which is a fun form of mathematics that you can do without actually having to use numbers, doing geometrical experiments with magnetic arrows and things like that, and maths of chance and all these things. Anastasia Popkova is going to be talking about how we're trying to introduce those things also at a very early age. So the net result of this needs to be that by the age of 14 to 15, all students should have a basic grasp of the concepts and the objects and the vocabulary of modern physics, because most students will cease to study physics after that age. And yet they are the voters, they are the people who will vote for whether or not we're going to have a scientifically based government, whether we are going to do things rationally or we're going to do things irrationally. And so the rationality of future decision making depends on us making sure that young people really do understand the importance of science and the relevance of science. So why have we got this problem, and how is it that we can solve it? A lot of this has got is a problem to do with popular media. It's not necessarily that popular media is bad, it's the education system has not kept up with popular media. And the other reason is a more theoretical one, that there are educational ideas that young children can't understand concepts until about the age of 14. And if we think back to the 1950s or the 1930s, atoms had never been observed. They were really conceptual things. They'd been deduced to exist, but they weren't seen. There was no sense of any experience for it. Today, almost all the things that were conceptual in the past are now part of our experience and are measured in experiments and able to be seen. So things that were considered impossible to teach in the 1930s, 40s, and 50s, today because of technology, they are all now visible and apparent and have changed from being really conceptual to being reality. We're quite sure that this is something that works, and we have results that it benefits student attitude, student engagement, and gender. And it's also low cost and quite easy for teachers to implement and teachers to enjoy. I'll show you some of that stuff at the end. But I want to just go into all of these points in a little bit more detail first. We've been recently running black hole workshops with 12-year-old kids coming in, and in a survey at one of these workshops, we found out that the mean age that children had heard of black holes was the age of 7. And we asked them to fill in questionnaires, and we asked a question whether they agreed with the fact that science taught at schools is mostly old stuff. And the 40% of them strongly agreed. Some of them were neutral, and just a few strongly disagreed. But these were a relatively exceptional bunch of kids who probably come from particularly good schools where they have teachers who are really interested in science. But in the average school, I think we would find that this was a more extreme thing. And the point is that there's more modern science in The Simpsons than there is in the classroom. And I want to show you a few examples of some of these things. There are some books called Horrible Science or something that many young children like. And this is 2 pages out of a book that I saw a 9-year-old reading just yesterday. And I quickly snapped some photos of these pages. Horrible Holidays, The Black Hole Hotel. Why not drop in for a whole lot of fun? And then it talks about basically gravity gradient effects and things of that sort. And then the neutron star hotel, and talks about the size of the atmosphere on a neutron star. Well, this is all modern stuff. And here's a 9-year-old who is, who's reading about this, but never hearing about it at school. In The Simpsons, Stephen Hawking was on The Simpsons. Homer Simpson says, in this house, we observe the laws of thermodynamics. Lisa creates a perpetual motion machine. Homer enters 2-dimensional space. Many examples there of science concepts that are way beyond anything that is ever touched on in the formal schooling that kids experience. And if you have a look at the science media that's out there, there's something called Project MC Squared. All kids know about E equals MC squared. Here's what somebody told me about what their 5-year-old son does on the internet and YouTube and channels that they look at. So kids experience all this science, and yet it's in complete conflict with what happens in school. And what's important is the explanatory power of Einsteinian physics. And when I say Einsteinian physics, I hope it's all clear to you that we use this as a label to cover all of the things discovered from around about 1900 or even the 1890s when electrons were discovered to general relativity. And atoms are a particular case of interest because today atoms can be viewed individually. Here's the IBM logo done in single atoms. And you can see movies and images of single atoms. There's a wonderful little movie called A Boy and His Atom, where atoms have been used to create a movie of a boy basically bouncing balls around. So the important thing is that the Einsteinian description has explanatory power. The fabric model of space-time explains gravity in a sort of intuitive way, even if there are, you have to consider what is wrong with your fabric model. How does it relate to three-dimensional reality? Because all these things are beyond our visual experience, we have to make use of models and things to do it. But within those models, everything works very nicely. So behind all this is the fact that modern technologies that were enabled by Einsteinian science changed the Einsteinian world from concept to fact. So atoms are not concepts, they're facts. Photons are not concepts, they're facts. So to summarize my thesis then, first of all, shifting paradigms is difficult, and we shouldn't force people to shift paradigms unless they absolutely have to. Early schooling is grounded in the Newtonian paradigm. Newtonian paradigm was falsified 100 years ago. It was a difficult battle of discovery to give us on the Einsteinian physics. Those stories of discovery of Einsteinian physics are actually wonderful stories that are very, very engaging to children and can be part of the learning process. In Australia, compulsory science ends in middle school, and I presume it's the same everywhere else in the world. Most people are locked out of modern understanding because they live in the old paradigm. And as I've said, anti-science is surely fed by this paradigm lockout. If you're in the wrong paradigm, it's so hard to understand the modern paradigm. So we've got to abandon the Newtonian paradigm in school education. Don't think that, it doesn't mean to say we don't use it as an approximation, but we abandon it as a way of thought. And most important thing is that young children happily accept this modern paradigm. But as I keep saying, it's difficult for the teachers. There's strong theoretical, a strong theoretical basis for these ideas. Jerome Bruner, who was an educationalist at Harvard, and is I think the father of the concept called Constructivist Education, said that any subject can be taught effectively in some intellectually honest form to any child at any stage of development. And within his constructivist ideas is this idea of spiral learning, where you start with something and you spiral around and build it up and go in deeper and deeper and deeper. And activity-based learning is the best way to do this. And another important document was a document called Taking Science to School, Learning and Teaching Science in Grades K to 8 by the National Academies of Science. Just a couple of quotes from that: "We are underestimating what young children are capable of as students of science. the bar is almost always set too low. Children come to school with the cognitive capacity to engage in serious ways with the enterprise of science. So we don't do that today, and we really need a revolution in science education. And then they emphasize again, children come to school far more ready and far more capable to be science learners than previously thought. A reason for renewed commitment to science education, and most importantly, an invitation to action on the part of researchers, school practitioners, and state and federal policymakers. I showed this slide to our National Curriculum Authority a few weeks ago. Another important thinker in this area is Kathleen Metz, and she says that science frameworks have frequently limited the content targeted for the early grades to such simple and concrete ideas that they offer little explanatory power. Even preschoolers seek explanation. We all know children always ask, why? If we teach them without answering the why, we don't properly teach them. So we're trying to create a seamless progression of learning where there is no change in paradigm. And in particular, primary school is a place where you don't expect children to really remember everything that they've learned, but they learn a way of thinking. They need to have their minds opened to expectations for the future, and they need qualitative and experiential activity-based learning. And then that can be consolidated in middle school and then developed into high school. So that's what we are aiming to do. And now to this question, how do we prevent teacher confusion? The new concepts are frightening, but the activities that we use for example, we use Nerf gun photons, and we use our lycra sheets where we roll balls around for gravity experiments. Those things are not frightening at all. So what we need to do is to put the activity first, and then let the teachers understand what's the concept that grew out of the activity. And if you put the activity first, the teachers are not frightened of it. They love the activities and they learn the concept from it. So that's what we've learned. It's taken us quite a long time to understand that and to create all the material that we present in that way, where we put the activity first and let the teachers become aware what the concept is. So here are just a few examples of how we've responded to the current primary school, things that happen in the primary school and how we overcome it. Primary school's got implicit flat space geometry. Well, we start our geometry off doing it on upturned woks and on balloons. Any curved surface where you can do geometry, you can survey straight lines on these curved surfaces, and you can get the idea of curved space geometry. For time, you can't do so many direct activities, but students can learn about how the clocks have to be corrected in GPS navigation because of the time differences, and can learn the idea that you get old quicker in space. And when you're climbing a staircase, you're climbing against a time gradient. Light's undefined in primary school. They talk about what light does, but they don't ever define what it is. Well, we get explicit and we talk about it, that it's a stream of photons like Nerf gun bullets. All kids love playing with Nerf guns. And so, this is always a huge amount of fun for the kids. And with those Nerf gun bullets, they get to understand that that these photons are things that have got momentum, that can push things as well, and even break things, and they also are discrete. But of course, there's something wrong with the Nerf gun photons because they don't go at a constant speed. So that has got to be made clear. You learn from the weaknesses of the analogies. Heat's undefined in primary school. Well, it's so easy to teach kids about atoms, and kids can be pretend atoms, and they can jiggle, and you can make a line. You can make heat move down a line of children where one child jiggles and jiggles the next, and the jiggling goes down the line. So you can get, and you can do things with all sorts of toy atoms as well. And we use rubber balls and beads and all sorts of different things to be toy atoms. We also have magnetic atoms. I'll show a picture of that, of things called snatoms that are being sold by the guy that runs the Veritasium videos, so that kids can play molecules like CO2 and H2O. We have songs about these things so that they get to learn the language of molecules and atoms. And I think everybody is familiar with the rolling balls on lycra sheets, which is the way we teach gravity, and also the geometry of curved space. I just want to introduce our whole team. I won't go through all the details of this. Rahul Chowdhury's just finished his PhD on teaching quantum mechanics and general relativity, particularly quantum mechanics for middle school. He's just published a paper in European Journal of Physics. And you're going to be hearing from 3 members of our team in other talks. And here is Kyla, who's got one of the upturned woks just here, and here is some further discussion of the topics that we cover. One, I won't say anything more about the curved space geometry. I've already mentioned about time being higher on high mountains or in space. The electric forces is something that is usually covered in primary school to some extent, or early middle school, but we try to create a unified view of that the forces associated with atoms that allow atoms to become solids are exactly the same as the forces that you experience with macroscopic magnetism and electrostatics. I think a really important thing, and something we haven't spoken about so much, is introducing de Broglie's Law, as I like to call it, which is, and there we explain it by saying that everything has got waviness and bulletiness. So we use these child-friendly terms, waviness and bulletiness, as qualities that all forms of matter have. And we try to show the sort of reciprocal relationship between, which is given in the famous de Broglie formula, that between bulletiness and waviness. And bulletiness, we use this word deliberately because it refers to destructive power, and it refers to something that, to carrying momentum and carrying energy. And so we then try to teach about the electromagnetic spectrum so that we can see that there is a transition point which is round about the optical spectrum, the visible spectrum, whereas above it, the bulletiness is starting to get very considerable, sufficient to damage our cells and things like that. Whereas below it, lower frequencies like microwave phone, mobile telephone frequencies, they have very little destructive power. They have very little bulletiness, and is dominated by the waviness, and they have very low energy. So this is a very important thing for people to understand. But then also we connect this to the maths of arrows because the maths of basically vector addition is what you have to do to understand how waves have interference patterns with maxima and minima. And even young primary school children get the idea of the maths of arrows, where we add up two arrows in the same direction to add up to 2 and the opposite direction to add up to 0. Here are some pictures of these magnetic toy atoms, which are relatively, their scales and everything is just about right, and they stick together just because they've got internal magnets, and allow kids to experience all those sorts of things. Here you can see a group of high school teachers who are learning how to use a space-time simulator. And in this case, they're looking at some figure 8 orbits between two objects. Another very important thing I think is the quantum to classical transition. What does it mean? Are some things quantum and some things classical? Well, there's more and more evidence that that's not really the case at all. There's a recent paper come out of gravitational waves where we can see the quantum behavior of 10 kilogram masses. Online, it's very easy to get patterns like this interference pattern, which is being created by single photons arriving in some locations and not arriving in other locations. So behind all this is quantum probability, and what we need to understand is that everything that we experience is probabilistic in this way, that the illusion of smoothness and continuity is due to the smallness of the quanta, whether it's atoms or photons, and the vast numbers involved. But the important thing is that everything is a few clicks away on YouTube, and as long as you can show teachers what to look for and how to find them, you can see the interference of molecules, the interference of atoms, interference of electrons, all sorts of things of that sort. And see, and then you can compare an image like the one we see here with the most photons with a photograph of an interference pattern where it looks continuous, but in reality, of course, it's not. So here's Anastasia, and she's going to be talking about our first trials on introducing maths for Einsteinian physics. So I won't say anything more about that. Well, I spoke wrong because I do have one more. I do have a slide to illustrate some of the things. Anastasia is very emphatic about using Fermi approximations. Children being able to work with approximations when you're dealing with powers of 10. Rough sums are okay, like 3 times 3 is about equal to 10. To my mind, is a much more important thing to understand than to know your exact times tables for rather large products that you can always do on a calculator. So we try to make powers of 10 very easy and teach that at a very early early age. And we introduced powers of 10 by, as Anastasia is going to explain more, by starting by doing powers of 2 before we go to powers of 10. And we allow children to experience that. But then finally, we can talk about, all the scale of the universe that we might ever want to discuss, which goes from only 124 different values for powers of 10, covers virtually everything in the universe, from the number of photons in the universe to the energy of a 1 Hertz photon, for example. And but we also get kids to work out things in relation to E equals mc squared, where we ask them to calculate what's Australia's total electricity usage in kilograms. It happens to be about 30 kilos a year. And the world's total electricity per year is around about 10 tons per year. So these are interesting sums that kids can calculate. And Sean is giving a talk about the programs that he's been developing for the year, for high school, middle school level, a year 7, where we're introducing a whole program on gravity and momentum and everything from black holes to orbits in the solar system and gravity on Earth and the equivalence principle. And also a year 8 program on energy, where we've taken many ideas from Friedrich Hermann. But I should say that maybe Friedrich might have some suggestions how we should better present that. We present the speed limit of the universe as an observational fact, but we also, in the year 8 level, we try to use the idea of E equals K times M, where we emphasize that C squared is just a constant of proportionality. And finally, we come to this question about Newtonian physics and about whether you should go from Newtonian to Einsteinian or the opposite direction. And the important thing is that it's much easier to go from the truth or our best approximation of the truth to an approximation than it is to go in the opposite direction. So architects and engineers happily make flat Earth approximations. It's no problem for them. People imagine that by teaching Einsteinian physics, they can't understand the approximations that we need to make in Newtonian physics. But at the same time, we do need to emphasize the weakness of Newtonian physics, that orbits are unstable for radius less than 3m, for example. We also use stories of discovery plays to allow students to understand how all the old ideas were overthrown, so how we actually got here to this understanding. This is our draft curriculum, just shown by titles. We try to make nice, friendly titles that kids will enjoy. Atom Frenzy, Hot and Shiny, May the Force be with you, Fantastic Photons, Our Place in the Universe, etc. So we have something that finishes in year 10, where we cover topics including climate change and cosmology. So I want to finish with, by just quoting an assessment that was written for our project from one of the year 7 teachers who's been trying it out. And she said this: the notable thing about the Einsteinian physics lessons is that the students are fully engaged, disruption is rare, and students with learning difficulties are practically indistinguishable from the mainstream students. The classes are easy to teach because the students are so engaged. And then she said, Einsteinian physics is interesting to everyone. Sorry, what's happened? Yeah. And it becomes much easier to talk to students about interesting things like the latest black hole discovery. And finally, she said, my classes include many students with mild to moderate learning disabilities. The lessons feature the modeling of concepts with hands-on concrete materials, an instructional approach that provides multi-sensory learning opportunities, allowing all students with learning disabilities to be successfully included, engaged, and educated in Einsteinian physics. I firmly believe that we must allow students use their bodies and not just use their heads and their eyes and their screens to learn everything. They must be able to learn physically. And finally, she says, from my personal point of view, this project is a fantastic initiative and one of the very best things that has ever been done for STEM education. Weaker students gain confidence and understanding by active participation and feel included. Girls benefit especially from the way the program is presented with group learning and activities. It's not intimidating, and teachers like myself enjoy the program because it makes my teaching feel much more worthwhile. So we were very pleased to hear that. Here's a list of our research papers. I'm not going to say anything about that. We've trialed our programs with around about 2,000 students, with around about 20 schools from years 3 to year 10. It's been universally well received. We've had positive research outcomes. I don't need to repeat that we are advocating this early introduction of atoms, photons, electrons, etc., as an explanatory scaffold. I want to say that we are happy to share our lesson plans once we've sort of finalized our quality assessment. We try out the lessons. We go through a great deal of assessment processes, also tests, pre-tests and post-tests and things like that. But we are happy to share that and to help others introduce these sorts of programs. We don't want everybody to have to reinvent the wheel. And we've made lots of little instructional videos, but nowhere near enough. We need to have a lot more. You can find all that on our webpage. Our book, Teaching Einsteinian Physics in Schools, which isn't just Einstein First book, it's from a lot of chapters from our group, but there are, I can't remember how many chapters altogether. Anyway, it's being published this month. And we're trying to raise funds from the public, from the private sector so that we can do more, in particular, so we can get some things online. And there's the cover of our fundraising brochure where we say, kids are losing interest in science, Australia's falling behind in STEM, and Einstein First has the solution. Thank you very much.
Thank you, David. Thank you for your beautiful introductory talk to our discussion. So we have time for questions.
May I make a comment?
Yes, Frederick.
Yes. Well, thank you, David, for this talk. I enjoyed it very much, and I made many comments about it. I could give now a question for 3/4 of an hour. We don't have this time. So I agree so much on many details of what you said. Exactly the same thing I'm telling to my students. Well, there are some points where I differ, that is the contents, but we don't have the time to speak about it now. Let me just add one detail. I'm an old man. I've been in many meetings, international meetings. By the way, we never met, I think, no? ICPE meeting, GREP, and so on.
No, we met at the in Germany at the
yeah, but Hornef.
Bad Hornef, yeah.
Yeah. But this last one, no, the 20, 30 years ago. Well, anyway, I just...
No, Bad Hornef in 2019.
I wanted to speak about an observation about these meetings, very big meetings, or the didactic community, international. And all of them, you had a lot of good talks, and they always proposed what we could teach in a modern physics course. But there was not a single talk, never, about what we can leave out. And you are the first person, apart from myself, who is speaking about that. And that's a very important point.
Oh, good.
Just let me finish with this. Thank you.
Okay, Andrew.
Hi, David. That was a really good talk. And on the whole, I think what you're proposing is a really good idea, but I did want to run two quick ideas past you. One is that you're aiming to address the sort of the anti-science attitude that's getting increasingly prevalent in mainstream society. And I think this will help with that, but I do wonder if there's some deeper root cause to that sentiment that will still persist even once this curriculum gets into place, and that we'll just find ways to adapt to it. And secondly, I wonder, I mean, we've seen from that anti-science division of society resistance to curriculum changes like this from the biology side, from the history side. There's been claims of indoctrination, sometimes political motivations. And I wonder if you're foreseeing any kind of pushback of that stripe to what you're proposing to change here. I mean, I don't think it's as likely, but I wondered if you'd thought about it.
The pushback usually comes from old physics professors who say you can't teach, you know, the Einsteinian until you've gone through all the Newtonian stuff. I haven't, you know, I've written quite a few articles, for example, in the conversation, where there's been plenty of opportunity for people to make comments of the sort that you are suggesting might happen. I don't think there have been any of those. You can go through and have a look at a couple of my conversation articles. Sometimes the comments are completely by people who just want to, who are sort of professional discussers of their own issue and want to use it for that. But there are many who say, I wish I had had an opportunity to learn this when I was at school, and can you bring your program to our school and things of that sort. So I'd say that we've really had almost universally positive responses, except, for example, the seminar I gave to the Australian Curriculum Authority reference groups all over Australia a few weeks ago, where there were two people who said, oh, they don't really learn what a photon is, or something like that. They just learn the word and they don't know what a photon is. Well, of course, nobody really knows what a photon is, but we can give them our best understanding of their properties. So there are always a few people like that, but really very small. I'd say 2 out of 50 in that case.
Okay, thank you. That's encouraging to hear.
Mm. Can I ask where you're from, Andrew?
I'm in Melbourne, Australia right now.
Ah.
Originally from Sydney.
Are you at Melbourne Uni?
Swinburne.
Oh, Swinburne. Are you part of Ausgrad?
I am.
Oh, right, good.
And I don't know if you know Rob Hollow, but I was involved at Posset Parks at CSIRO up until recently.
Oh, I see. Yeah. Well, we must talk some more.
Look forward to it.
Okay, thank you. So you go to the next speaker, is Sean. Sean, you can share your presentation, start when you want.
Sure. Second. Can everyone see the PowerPoint slides? with
Sean, probably you have to switch to
It's not on full screen. I don't think you have.
presentation view.
okay. I did. 1 second. Maybe I'll change it. What about now?
You should do play show.
Second, I'll do this again. Okay, there you
That's
go.
right.
Okay. Actually, no, but this disrupts part of the setup that I had. Second.
Oh.
Just give me a second. There you go. Okay. You can see the full screen. We're teaching the equivalence principle in year 7. Everything's clean. Okay, perfect. All right. Yeah, so my name is Sean Char Balil, and I'm from Canada originally, but I came to Perth, Australia to be part of the Einstein First Project, which is a bold project that is trying to be revolutionaries in the field of STEM education. And our goals is mainly to develop a concise structure for a curriculum that goes from year 3 to year 10 in teaching Einsteinian physics. So it's based on trialing lessons, having ready-made lessons that are easy to use for teachers, hosting a lot of continuous professional development in collaboration with the teachers, organizing interactive workshops at conferences, having meaningful conversations with teachers and members of the research group, working collaboratively and giving feedback and going through this whole process of reconstruction in order to get concise lessons that clearly state what needs to be learned in each lesson. Here's a picture of a workshop that happened recently, and it kind of portrays the free fall experiments that we will explore soon. So, second, yeah. So, when designing the year 7 curriculum, we asked ourselves, how should a proper progression and connection between the concepts be chosen for year 7? And this order was gradually built with members of the research group. We started first with, in the first chapter, measuring space, where students start learning about the concept of straight lines and curved space. And then we relate this particular concept to the idea of space-time, where students understand the concept of the speed of light, have a feel for what is speed and acceleration. And then after that, in chapter 3, we go into free fall. And this is associated to Einstein's equivalence principle, his happiest thought. And this directly relates to the space-time simulator that we decide to use in chapter 4. And we learn a lot of things about this model, some of the inconsistencies, but at the same time, it allows us to have a deeper connection into the history of science and to theories in physics, including Einstein's, Kepler's, Newton, and etc. And with this knowledge about cosmology and the grand scheme of the universe, we go into the forefront of physics and looking into black holes and gravitational waves. Yep. All right, my screen, oh, there you go, okay. So while the whole study investigated approaches in teaching Einstein's theory of gravity in year 7 within a whole curriculum structure, this presentation will mainly focus on lesson number 7, which is to investigate Einstein's happiest thought, where students predict, observe, and explain the behavior of 4 different objects in free fall. So the research questions associated to this lesson are what approaches were taken in the design of the lesson? What are the learning outcomes for students? how do the situations presented allow students to develop an understanding of the equivalence principle? What mental models are used by the students and also by teachers in understanding this first instance of Einstein getting an idea of how to come up with theory of gravity? So in designing the lesson, we needed to take into account approaches that promote conceptual change. So many researchers agree that there are many teaching practices that promote conceptual change. And here is probably a list of the most popular ones. One is to get students to solve problems, go back to concepts and reuse them in different contexts, allow students to express their designs, invite students to manipulate with objects, hands-on objects, that consider also that conceptual change and understanding from one point of view to another actually takes time. And this is what the whole curriculum tends to do. It's a whole process of going from one perspective to another. Also, we pay attention to the epistemology of the sciences that is represented while teaching. And at the same time, we encourage discussions in the classroom with the teacher and peer-to-peer. So let's go straight into the lesson. What are some of what do educational research say about teaching Einsteinian physics, and especially the equivalence principle at this year level? So in order to give way to new ideas about physics in classes, lessons should portray the rupture between Newtonian and Einsteinian physics. And we see many research that talk about this particular concept, especially in Ekdal's 2009 paper, where he teaches general relativity to the layman, and he states 3 issues with Newton's gravity. One is, how does a massive celestial object such as the sun hold the Earth in its orbit? The other one is, space intervals change with relative motion. And the other one is Newton's proposition that gravitational disturbances travel instantaneously through space, which violates Einstein's first postulate of relativity. So do we consider all of these 3 issues when teaching the equivalence principle and freefall at the year 7 level? Well, when thinking about it, we decided to only opt for the 2 main issues, which is this fictitious force, this invisible force, and the violation of Einstein's first postulate. So this is how the lesson goes. And this, just to state again, we're talking about year 12 students. And as in David's talk, we've seen that, in these classes you have students with mild ADHD. Some have problem writing. There's yep. Okay, so you can see this. Okay. All right. Perfect. All right. So Einstein wondered why objects of large inertia fall the same way as objects with small inertia. And just to go back to what I was speaking about, I was showing how a researcher was using Newton's issues of Newton's gravity in relation to teaching Einstein's theory of gravity. So he wondered why objects of large inertia and objects with small inertia fall the same way. In 1905, a few years later, he noticed that nothing travels faster than light, and this is the speed limit of the universe. In Newton's theory of gravity, it says that there are instantaneous forces between objects like the Earth and the sun. And if the sun suddenly disappeared, Newton's theory says that Earth instantly starts moving in a straight line from its orbit. So this instantaneous interaction between two masses. Einstein says that it was impossible for that to actually happen because it would take actually 8 minutes for this information to travel from one place to another. So in the same scenario, same thought experiment, if the sun disappeared, it would take 8 minutes for that to be true. So here there are the two inconsistencies in Newton's model in order to understand and want to understand a better view of gravity. And it also shows that gravity travels at the speed of light, which is important for understanding gravitational waves, which is seen further in further lessons in the year 7 curriculum. The other one is when we start talking about the introduction of free fall and the introduction of Einstein's happiest thought, where free fall is any motion where the Earth is not holding you up. So in free fall, you're completely weightless. The other idea associated to this free fall thought experiment is the accelerated reference frame, which was written in his published in his paper of 1907. The thing is, if you think about an accelerated reference frame, there might be one common misconception that might arise from this, is that an accelerated reference frame actually generates gravity, and this is not the case. Einstein's thought experiment can be seen as a situation where an accelerating inertial reference frame creates gravity. However, gravity remains an expression of curvature and is not generated by it. So there is a simple way of demonstrating how the inconsistency with the accelerated reference frame. One is if you decided to drop two balls in an accelerating elevator, the balls would drop parallelly. And if you would drop these two balls in a gravitational, in curved space-time, then you would have them actually converging and getting closer to one another. And this has been shown in many books, and we do introduce this to students. Now, after the instruction part, after the introduction to Einstein's happiest thought, we decided to use a few objects in teaching this particular concept. So most studies that I've looked at online only used one object to predict, observe, and explain the behavior, their behavior in free fall in association to Einstein's free fall thought experiment. In this study, we decided to use 4 objects that students investigate in free fall. This allows for the learners to revisit the concept of free fall and weightlessness and use their prior and current developing conceptions to make better predictions of objects in free fall. This, I think, this repetitive process reinforces concepts that are associated to Einstein's equivalence principle. So when looking at the approaches that promote conceptual change, we see that the reason for having these 4 objects actually is to reinforce approaches that promote this conceptual change from one point of view to another. So solve problems, reuse their understanding of the of free fall in different experiments. They express their design, they manipulate and we encourage them to talk about what might happen when we drop these 4 objects. One being a leaking cup. Poke a hole in a cup and you have water flowing out, a suspended slinky, 2 magnetic rings on a stick that are repelling each other, and tape measure masses, where you take a tape measure and you add 2 masses on each end, and you ask them to predict what and observe and explain what will happen. And this notion of predict, observe, and explain has been used in research since the time of Novak. I think Nussbaum and Novak were the first ones to find what are students' thoughts or like young students' thoughts in understanding gravity, and they use this particular model to understand students' conception. So this notion has been used widely in education. So one of the things is that in order to explain these concepts to teachers, we really need to make them consider all of the forces that are in play for each particular object. So when you drop the objects, they experience no force in free fall. So when dropping the cup, water will not leak out because both the water and the cup are falling at the same rate to the ground. The bottom end of the wooden rod is holding the bottom magnet from free falling and being repelled by the top magnet. So when you drop the whole device, the only force that the object experiences in free fall is magnetic. When letting go of the slinky and the measuring tape, the only force left is the spring force. So you have dropping the 4 objects. And doing this in slow motion actually helps teachers understand this particular concept. They actually, sometimes it might be slightly too fast for them to see what exactly is going on, because there are several things to consider when looking at these experiments. However, they have great explanatory power in understanding free fall. So one analogy, one maybe extra analogy that could be used in this scenario is the analogy between the slinky and the vanishing sun thought experiment. And it can reinforce the idea that disturbances in gravity do not happen instantaneously through space. So the contraction of the slinky demonstrates that, that this idea that, nothing travels faster than the speed of light. So over here you have the sun. The slinky represent the gravitational interaction between the sun and the earth, and letting this go, well, you've seen what happens. And it reinforces the concept that gravity travels at the speed of light. So now, what are the mental models that were used by students in this particular lesson? So students could either write their answers, or they could actually come up with a diagram in order to show the behavior of the object. And this was actually effective for students that had maybe a hard time writing exactly how the magnet either would go up or would go down. And I think some students really prefer to use them in many situations. But most of the students did accept the concept of weightlessness and free fall, which is essential for understanding Einstein's equivalence principle. However, one of the teachers recommended that the idea of the analogy between the gravitational interaction between the sun and the earth should be used immediately after the slide of Newton's disappearing sun. And this had maybe a reverse effect on the explanatory power of the model and the idea of free fall and spring force. They actually used the explanation of the sun to describe why the slinky behaves in this particular fashion. So there is a time and place for using analogies, and the best way to use this analogy is towards the end of the lesson to reinforce one of the concepts that was initially introduced. So in this series of lessons, we tested this lesson with many teachers, but I will mainly show 2 class samples. So one post-test was administered after 3 to 4 lessons, and the second post-test was administered after 8 to 9 lessons. So all of the students, I mean, not all, but most of the students understood that gravity travels at the speed of light. When looking at free fall conceptions in association to the post-test, many students got it right, even along the way. And the results of the complete Year 7 curriculum showed an improvement in students' understanding of Einsteinian physics, and well, they better understand, Einsteinian physics if you're more exposed to it. So it's important to have this complete curriculum sequence. And I will end this talk with responses and discussions from teachers. So objects in free fall are not feeling a weight force. I needed first to consider what would happen if gravity was not around. How would these objects behave? You need to imagine and feel the tape measure magnets, slinky, and consider the forces present in the object you are holding. What would the object be doing in space? Making the connection between all the forces took some time to understand. Why is the magnet going up is something that I considered initially. An object not experiencing weight was a difficult concept to accept at first. However, its association to outer space was central. I think a discussion of the forces that are present could help many teachers in understanding what is happening. Here's another discussion between the teacher.
You have 2 minutes left.
A few minutes, perfect, okay. So here's another discussion between the teacher and the PhD student. And okay, so student, accept that you don't sense the force of weight in free fall, only sense it. This is important because, well, it tells us that we are in an inertial state, like floating in deep space, or the idea that planets are free falling. This idea is important for understanding gravity, which is the curvature of space-time. We experience no weight when we are free falling in curved space-time. We are following an inertial path through space-time. And the conversation continues. How did the equivalence principle lead Einstein to posit that gravity is the curvature of space-time? The point of getting students to release all of these objects is to get students to accept that you don't feel weight in free fall. What is the connection between accepting that objects in free fall are weightless and the curvature of space-time? Really good question, and it's not simple to answer this particular question. You have to resort to other models. So planets move inertially, not feeling any weight in curved space-time. Einstein gave a reason of why all objects appear to fall the same way. They are following a straight line path through space-time until they encounter something that stops them, like the surface of the Earth. So to visualize curved space-time, I needed to resort to models that are used online, and especially by the group in Norway in the learning module developed by Magdalena Kirsting. So I will end this talk with just a short
It's mind-bending science.
video from...
What does matter do exactly to this space-time?
With the help of a space-time simulator, these Year 7 Mount Lawley Senior High School students are learning Einsteinian physics.
We've been learning about how space-time tells matter how to move and matter tells space-time how to curve.
And while generally not taught till university, those involved in the Einstein First Project hope that will soon change.
Every kid has the right to share the best understanding of the universe. So we are developing some hands-on activities to teach the concepts of general relativity, special relativity, and quantum physics.
The current science curriculum in schools relies heavily on Isaac Newton's discoveries around gravity and the laws governing motion, discoveries Albert Einstein later proved problematic.
So I will end with this, and thank you so much. And this was teaching the equivalence principle at the Year 7 level. If you want to find more information about the project, here's the website, and this is my email.
Thank you, Sean. So we have time for just one question.
Yeah.
Conceptual changes take time. This is a comment on what he said, but not only conceptual changes. Everything takes time to be understood. I mean, your curricula, your lectures are not something that is made out of the blue in 30 seconds. Each lecture has 1 century of experience before. That's my consideration.
I agree. I totally agree with you.
I may be able to do one of your lecture by myself. The other.
Okay. I might add, kind of like from an experiential point of view, the enactment of the lesson, kind of doing the lesson once, allowed the teachers to repeat the lesson in 4 of their other classes. And I decided to use this model with a few teachers, where I teach the lesson once, and they were comfortable enough to teach the rest of the lessons. And even though some concepts might have seemed slightly foreign or not too clear, they realized that there are a lot of concepts that students accept. Just accepting gravitational force, we accept so many things without thinking about it. So the point here is to create a dialogue and teaching Einsteinian physics, and push forward new ideas and teaching it at the lower level. Yeah, but I might ask, what is, you said the conceptual change takes time, but I see myself only using one of the lessons to teach my students. Are you a teacher in middle school?
Yes, I am.
Then I'd be happy to organize a workshop for you, association to this. Yeah.
Okay, so we can make a further discussion soon. So we hope that we don't have any stops from the system, but in any case, we will have some backup time at the end. So let's go to the next speaker, Anastasia. So you can start sharing your screen and start your presentation if you're ready.
Hello everyone, I'm trying to do it, to share my screen. Is it everything okay with it?
Yeah, it's fine.
I need to do, yeah. Is it good sound?
Yes.
Yeah, I can't hear anybody, but so let me introduce myself. My name is Anastasia, and I moved from Melbourne to Perth recently to be a part of Einstein First Program. And today I would like to represent a mathematical program for teaching early high school students about black holes. Einsteinian physics has been considered too tough and hard stuff to comprehend for school students for many, many years. And what could we talk about mathematics? But general success of Einstein First Project encouraged us to develop some sort of supporting mathematical curriculum called Math for Einstein Universe. I don't know why I have this Windows here. Maybe I could change. Yeah, so it consists of 3 parts which connected to learning about big and small numbers, theory of probability, and vectors and geometry. So, and we should say it's not only for special Einsteinian physics learning. It's also very relevant for modern world with problem like population and pandemic spreading, climate change, world of money, and it's just only a few issues here. And today I would like to represent just small part of this program. It's a mathematical curriculum or part of curriculum for 12-year students about learning about big and small numbers for black holes. We had Discovering Black Holes workshop. It was during 4 weeks with 2 hours per week. And we have part of mathematics approximately for 2.5 hours. We have mainly students from year 7 to year 8, but also we have gifted students from year 5 as well. So, why we need this type of learning about big and small magnitudes? There are the issue we raise on our black hole workshop, like stiffness of space, cosmological timeline, gravitational wave strain detection, energy, astronomical distances and masses. And it was proven by researchers that we have special challenge in the area of big and small numbers. Students, school students, and even adults tend to overestimate big number, underestimate small number, and they cope with proportional reasoning in this area. That is why we have special supporting learning. Paying attention to all this issue, we form learning outcomes we want to have from our students at the end. It's knowledge about the scale of the universe, because in order to reasoning about big and small magnitudes, we need to know about it. Second, it's developing exponential thinking, because it's only way to demonstrate small and big numbers on the one line. The developing of exponential thinking includes writing the number in powers of 10 and also operations with this number. The another outcomes, it's about estimation and approximation, called Fermi estimation, because we need to explain children what is important when we comprehend about number, what is not important. And the last but not the least, it's proportional reasoning, because often for us, really big numbers like the trillion, billions, it's more word than numbers, and we can't make any differences in this area. And here's photo from workshop. Our students happy with certificates, and we are happy with outcomes we have. So this slide intends to demonstrate that we have 2 or 3 activities for every outcome we want to get. And I would like to give some more detailed information about every activity. So the first one, aim to go from linear thinking and linear scale we always have in the school to exponential thinking. And we have quite physical activity where when our students measure their heights in the group of 3, and then they lined up to discuss the difference between the smallest one and the biggest one, to understand proportionality in this linear scale. And then after that, we mark these numbers on a string. We had string initially like 1 or 2 meters. And then after that, we stretch it to 10 meters, which is 10 to the power of 1. And this fraction looks much smaller. And then we stretch our string to the 100 meters, which is 10 to the power of 2. And this fraction looks even more indistinguishable in this scale. What about the scale of whole universe? We use the famous movie Powers of 10 just to give children information and knowledge about real scale in our universe. And through this film, we move from our 100-meter measure tape, not measure tape, just paper tape, to the scale of the universe to understand what place the human size have at the scale of the whole universe. The second activity was aimed to develop and enrich our exponential thinking. We divide our children into groups. One group did halving of 1 meter IKEA measure tape, and they were asked to write the number of cuttings we did, 1, 2, 3, and number of pieces we have if we cut every piece. This is some sort of connection between small magnitudes we have at the end and huge number of pieces we cut. So, as you can understand, this group just explore powers of 2 and rapid halving decrease of magnitudes. And another group did the same things, but they cut measure tapes on 10 equal paths. And then we give our children, they figured out that by the 10 cuttings in 2, we will have nearly the same result like 3 cuttings in 10th. And after that, both groups just did imaging experiments. How many cuttings should we do to go to a really small number? For example, to the size of the atoms. We say of course we can't cut our millimeters piece, but what we have if we could do it. So it's the second activities about powers of 2 and powers of 10. Next activity was aimed just to explain children how to work with numbers in powers of 10, how we could operate with powers, that we could do subtraction and addition of powers to make division and multiplication of our numbers. And there is a very funny game. We had a competition. So this is the rules. We need to obtain some target number, which of course was connected to some learning about black holes. It was gravitational wave displacement observed in the laser interferometer. And we had starting number as well. This is approximately size of the atom. And through the rolling dice, we went through one number to another number. We had 2 numbers, and we could subtract or either add our powers to get the result. Just some example how I did it. I decided to subtract two numbers I have at first rolling, and then I do addition and subtraction, just ignoring a bit theory of probability. And one of team went to this number first. So another activity is connected to proportional reasoning. We just continue to develop our division procedure and multiplication procedure, and we compare some object in the small area. I've already saw a picture because it's the funniest part. So, and children did this operation to figure it out what power here in the number connected to the size of the object, and how much time it's bigger from our target number, to understand how different the small object could be. So the next slide and next activity about estimation and approximation. In order to operate with big or small number, we just cutting some part, unimportant part of our numbers to do calculation. And this task called Fermi estimation, it's called after the famous physicist Fermi, who estimated the power of a nuclear explosion with 2 pieces of paper. And he developed this method saying better be approximately right than precisely wrong. And this method connected to a back of the envelope calculation. It's how I prepare these activities for workshop, just doing some rough calculation. And with children, we practice this type of problem, counting from 1 to the million. The question was, how long does it take to count to the million? And doing some estimation, they had the answer. And the next activities, just extension of these activities, we gave knowledge to children about lifetime of different stars with different masses. And we asked children to do experiment, how long does it take to count every year of lifetime of different masses through the Fermi problem, through the estimation. And they were very surprised to know that one big number like a million take just days to count to, and another big number like billions, it's almost impossible to count. It's not almost, it's impossible to count to the billions. And it is demonstrate how lifetimes of stars different. So, and second activities, it's aimed to compare some big numbers like speed of light with real life numbers like speed of car. Our children had a task to estimate through the drama story, through storytelling, how long does it take to travel to the moon by the car, if they know only the speed of light and time for light to travel to the moon. So they just make some certain plan, what car they will use, how many friends they should take in this journey, will they sleep or not, and another thing. So, and this is some brief trial program results. We're happy to mention that all of our 100% of students started to use powers of 10 in reasoning, calculation, and estimation, comparing with the 27% of students at the beginning. And 45% of students started to use confidently the wider range of objects like astronomical masses and sizes of atom and so on. In conclusion, I would like to emphasize that this particular part of program was developed and we have trials with 12-year students. We mentioned improving of understanding of big and small numbers, and we intend to include this part in a part of our main curriculum. Thank you for your attention, and we will appreciate any suggestion or approach we could use for this goal.
Thank you, Anastasia. So, are there any questions?
I have no sound.
Well, We can hear you well. Can you hear me?
Oh, sorry, probably I need to reconnect.
We could keep questions until after the next talk.
Yes, I totally agree. So we can go to the next speaker, Ritik Roy. So I don't know if he's able to share his presentation or it will be done by Jyoti.
Let me try this.
Okay.
Can you see it?
Yes.
Okay.
Yes,
So
okay.
should I start?
Yes, of course.
Okay. So hello, everyone. My name is Ritik Roy. I'm currently pursuing my master's in physics. And I'm going to talk about this proposed collaboration between Einstein First and LIGO India, which for now we're calling Einstein First India. So I guess everyone already has a good conception of what Einstein First Project is and what they're doing. But I'll still go over briefly an introduction of Einstein First and discussing a bit about the success and the results of Einstein First over the past 10 years. I'll then give a brief introduction about what the proposed collaboration is and its implementation in the initial phase. I'll conclude the talk with discussing the common goals of the LIGO India Education and Public Outreach Team and that of Einstein First India. So Einstein First is obviously a group of physicists, educationalists, and PhD students who are developing innovative methods for teaching school children the concepts of Einsteinian physics. It's also an international research collaboration, along with partnership from educational authorities from Western Australia and primary schools and secondary schools, who are trying to implement this sort of Einsteinian curriculum among school children. Their aim is to redesign, evaluate, and optimize school science curriculum across all educational levels to reflect the modern understanding of space, time, matter, and the universe. So over the past 10 years, as we already saw from Professor Blair's talk, that the Einstein First Project has shown that primary and high school science can be taught within an Einsteinian frameworks. Students have been shown to comprehend Einsteinian physics, have an understanding of derived concepts, and retain conceptual ideas of Einsteinian physics over a long period of time. And there has been considerable improvement in students' attitude towards physics, especially for female students. Now, the question is, well, why India? India has one of the largest education systems in the world. I think it's the second largest education system in the world with over 1.5 million schools, or 8.5 million teachers, and over 250 million students. It also has a strong history of students going for tertiary education in science and technology, with almost 1.1 million students going for tertiary education in science and technology every year. There's a steady increase in the number of students going for graduate schools abroad in different countries like US, UK, Australia in the past 20 years. India is also a future member of the LIGO collaboration, and with the construction of LIGO India underway, this makes it quite timely to try a program like Einstein First in India. There's a lot of diversity in India also. 28 states and 7 union territories, each having a student with different linguistic, cultural, and socioeconomical background. And this lets us test the hypothesis of the universality of the understanding of Einsteinian concepts among students. So Einstein First India is a proposed project planning to implement the curriculum of Einsteinian physics among school students in India. In collaboration with Einstein First, we plan on implementing the previously developed curriculum that has been developed by Einstein First over the past 10 years. develop newer curriculums, and also create an international research collaboration to study the implementation of Einsteinian physics among school students across both countries. In association with LIGO India, or more precisely the Education and Public Outreach of LIGO India, we plan on implementing these curriculums via regular teaching sessions and workshops among Indian school children. And as mentioned before, we'd also like to test the hypothesis of the universality of the understanding of Einsteinian concepts among students coming from various backgrounds. So for the initial phase of the program, we plan on initiating with what we are calling as an optimal student group. Because of the COVID-19 pandemic, India is still operating, the school system in India is still operating in an online medium. And hence, for the initial phase of Einstein First India, we might have to continue the program online. And it has been shown by several studies that smaller age group children has had difficulties concentrating and focusing in online education. Oftentimes, parents have to accompany them during their sessions to actually help them concentrate better. So that's why we are aiming for the middle school students, which is somewhat standard 7th onwards. And this is what we are planning on introducing the Einstein First India program in its initial phase. The syllabus of these grids also introduces the concepts of Newtonian dynamics, kinematics, and rectilinear motion, light. And hence, it would be good to contrast these concepts with that of the Einsteinian physics. We plan on introducing a single session with the students and teachers to spark interest towards Einsteinian physics. Previous studies by Einstein First has shown that these short interventions can raise the interest of students towards a program like this. These sessions would be complemented with an attitudinal assessment of both students and teachers. And the data from this assessment could be used to approach the authorities to discuss the possibility of regular long-term sessions of 5 to 6 months. We plan on studying the results of the students' understanding and feedback from students and teachers from the initial phase. And in case of non-optimal results, we would like to improve the literature, models, or activities and re-implement the single session. With the optimal results, we plan on training a few teachers and take long-term regular sessions of 5 to 6 months. We provide the teachers with models, analogies, videos, and activities to teach the students. Again, these sessions would all of these sessions would be complemented with the assessment that would test the conceptual increment of students after every session. And based on this data, we will conclude the effectiveness of the program among Indian school students. One of the important aspects of obviously implementing the program is to actually prepare the curriculum. And especially since we also want to implement an online curriculum as mentioned, both due to the COVID-19 pandemic and because of the large number of students in India, an online education platform helps us reach more students. We'd like to prepare a separate curriculum from both the online and the offline sessions. And a literature review on both the science syllabus and the review models and analogies that has been developed by the Einstein First Project for the past 10 years would be followed by devising new models and activities that could be implemented and by the teachers themselves. And the next is the initial sessions would help us to actually gauge the knowledge of the students on Einsteinian physics, and this would help us to devise these newer models better. So LIGO India has a very active education and outreach team, and their interest is to create awareness about among science and engineering students towards gravitational wave science. They're also working on maintaining continued interest and creating awareness about the LIGO India project amongst the general public. They're conducting several sessions with school students and different local communities, along with governmental and service organizations, to increase the awareness about LIGO India. The introduction of a program like Einstein First could create the groundwork for the introduction of the LIGO-EPO outreach programs. The studies conducted by Einstein First India could also help the LIGO-EPO team to create better resources for the gravitational wave workshops. Not only that, but a gravitational wave workshop followed by the introduction of a program like Einstein First could help the students understand the concepts of gravitational physics even better than just done by the LIGO-EPO team. Thank you. If anyone has any questions, please go ahead.
Okay, thank you. So we have time for questions, both for Ritik and Anastasia.
Ritik, I just want to say very nice talk and a really comprehensive set of plans and really well developed ideas.
Thank you.
Yeah, so hopefully at the next Master Grossman meeting, we will see some results from your trials.
Yeah, hopefully so.
Hello, I would like to ask a question to Anastasia. This program that you have for students, is it done outside the normal schooling hours, maybe during the vacation?
We did during second semester. We had workshop once a week on Thursday during 2 hours from 4 p.m. to 6 p.m.
Yeah, it's during school days. Yeah, yes, during school days and after school hours.
But we were using the Black Holes Workshop as a vehicle for trialing the programs which are going to be taught within the classrooms.
Okay.
Thank you for your question.
I sent a reference on the chat for Enrico Fermi, the estimate of numbers and of the accuracy of the experiment not beyond the necessary. I signal a very huge biography by David Schwartz. I can send
very beautiful. Yes, very. I know that book is a very wonderful introduction to life and work of Enrico Fermi. So very, very good suggestion. So, okay. So the next speaker should be Carlos.
Yes. Hello, everyone. Can you hear me?
Yes, of course we do.
Okay,
You can share your presentation and.
Okay, so that should now be in full screen, right?
Yeah.
Okay, excellent. So thanks very much, and thanks especially to the organizers for accommodating my schedule. So yesterday I had a busy day with other things, so I asked to be moved to this morning. Okay, so my name is Carlos Martins. You can see my email on the slide. So I'm a senior researcher at the Center for Astrophysics in Porto. I'm a cosmologist by day, so to speak. I work on projects such as Euclid, LISA, and various European Southern Observatory instruments. But I'm also the coordinator of the training unit of the Center for Astrophysics. We have the peculiarity of sharing the building with the Porto Planetarium, and it's actually part of our contracts that we're supposed to help the planetarium staff with education and outreach. So what I want to do today is to tell you about the AstroCamp, which is a project that I created about 10 years ago and which I think is going quite well. Okay, so what is the AstroCamp? Well, it's basically an academic excellence program that takes place in the summer. It always lasts 2 weeks. So the idea is that we select some bright high school students and we isolate them for 2 weeks in the mountains in the north of Portugal. So by choice, the students have no access to internet. They don't have mobile phones except for a couple of hours in 2 days of the week to call their parents and tell them they're okay. So we want to focus them on learning as fast as they can. So in addition to giving them high quality training in science topics that I'll come to in a moment, we of course want to stimulate further their curiosity and skills such as critical thinking, group responsibility, and so on. And of course, it's also a venue for high school students to meet other students that have the same aspirations, the same goals, even when they come from very different backgrounds. How does it work? We can only do this clearly in relatively small groups. So for this reason, the camp is selective. There's an application process. And the second stage of the application is an interview that we always do in English. And this has been always the case, even in early years when the camp was always was only open to Portuguese students. And one of the principles of the camp is that for students studying in Portuguese schools, whether or not their nationality is Portuguese, the camp has no costs. So we need to find funding every year for this. From 2016, we accepted applications from outside Portugal. And for those, we cannot guarantee a free camp. We try, of course, but it's written in the statutes that if there's no other source of funding available from our side or from the student school or municipality or whatever, the students will not pay more than 400 euros for food and accommodation and everything else and insurance in the 2 weeks. So that's our principle, if you want. What do we do in the camp? Well, we have classes. So students always take 2 courses, each of which has 10 classes of 90 minutes plus a written exam at the end. We have observational projects. So we are in the middle of the mountains. The sky is very clear. We can observe the sky. We have a computational project where the students learn scientific programming, data analysis, and so on. And then we do a bunch of other things. We watch geeky documentaries. We do community service projects. I'll mention one later on if I have time. We go hiking and so on. And we try to follow up the students after the camp. So in a lot of situations, projects that we start during the camp are continued by the students later on. And one example of this is actually the computational project. So as I said, the main goal is for the students to learn scientific programming, but we try to introduce this with reference to current research. And actually, some students go on to publish scientific papers as a result of work that started in the camp. So here's an example. So all authors here have been involved in the Astro Camp. So Ana Catarina Leite is my PhD student. She was a camp monitor several years. Catarina Alves and Tomás Silva were camp students and later camp monitors. And by this stage, they were undergraduate students in Porto. Siri Berge was a Swedish student that participated in the camp when she was in 11th grade. So when this paper was published a few months later, she was still in high school. So that's her high school affiliation. And Beatriz participated in the camp in the last year of high school. So when the paper was published, she was already in university. Is a second example. This is the same Beatriz who was camp monitor the following year. And this is Francesco, who was an Italian student who again participated in the camp in 11th grade. So he published this paper while he was still in high school. Okay, so here are some group photos of the first 4 years. So it's basically the students and camp monitors. I'm usually behind the camera in these group photos. So just to give you an example of the 2021 editions in terms of numbers, so statistics of applicants, we usually have more girls than boys applying. That has been a trend essentially in, I think, 8 of the 10 years of the camp. This year we have about 2/3 of applications from people studying in Portugal, 1/3 from abroad. This is actually not typical. In pre-pandemic years, the numbers were about 50-50, but clearly in the current situation, the idea of traveling to a foreign country is perhaps not so reassuring, especially for parents. The vast majority of applications come from public schools. And in terms of school grades, so About 1/3 come from 12th grade. So last year before university, about 50% from 11th grade, the year before that, and 20% from 10th grade. So this year we'll have 3 teachers. In addition to me, we'll have teachers from the Perimeter Institute and Trieste Observatory. By construction, by design, since this is a University of Porto education activity, teachers must have PhDs in the relevant area and must be currently active in research. We'll have 5 camp monitors, and this year, as in almost all cases, camp monitors are former camp students who are now in university doing undergraduate or master's degrees. So there's a continuity, and also former students, of course, know how the camp works, know what difficulties students might have, and so on. And we'll have 15 students. The Paredes do Coro municipality, which is where the camp takes place, can always nominate 1 student from their school to participate. All the others are selected through this interview process. And here you can see the country distribution. About half of the final participants are Portuguese. And again, we'll have 10 girls and 5 boys. This I can comment later if you want on why we have more girls in the camp, why they might apply more, and so on. I think I have some insights. In broader numbers, so if you put together the numbers from 10 editions, so here I've separated the first 4 years where we only have Portuguese students, and then the rest of the years. So we typically have comparable numbers of Portuguese and foreign students participating. So these are selected students, not ones that apply. Slightly more 11th grade students than from other years, and there's also good reasons for that. And again, slightly more girls than boys. And I should emphasize that we don't have quotas for any of these items. There's no quotas for Portuguese or foreign students, no quotas for girls and boys, and so on. So scientific merit and potential, to the extent that we can assess that in the application, are the only selection criteria. So it's kind of nice that the numbers work out to be reasonable ones, but it's what happens is not because we designed it that way. So here's 4 more group photos. And let me come to the point of relativity that is sort of the focus of this session. So one of the camp principles is that students are involved in choosing the courses that we'll take in the camp. And we do this in several stages, more or less in parallel with the selection of the students. So first we put out the call for courses, we send them to our contacts. So any researcher can propose to teach a course in the camp. We do a check of scientific and pedagogical content. So we check that it's appropriate for the age and the level of the students that we typically have in the camp. Then we send these information, so the course syllabus essentially to the students, who are asked to rank the courses in a blinded way, so they don't know who the teacher is. And then we look at the student preferences and take that into account and assign the courses to the students. So depending on the year, so if all the students vote for the same 2 courses, then we'll just have 2 courses and all the students will take the same 2. In other years, when there's more scatter, we can have more teachers. So this year we'll have 3 teachers and different students will have different pairs of courses. So once this is done, we also tweak the courses a little bit to make sure that the courses complement each other, but there's no significant overlap. So relativity is interesting because anytime a relativity course was proposed, so either a full course or a significant fraction of the course, say at least 3 of the 10 lectures, the students always selected it. It always came in the first or second place in the ranking. So clearly, it's a course that students want to have. So these are bright students, so they are not a random sample of high school students, clearly. But students do feel a need to learn more about this. And when you talk to them and ask, why do you vote for this course? Well, they say, well, it's cool, I'd like to know about it, and so on. But they also say one other thing, which I think is important. They say, it's a kind of topic that if I ask my school teacher, he or she will not be able to help me much. So essentially, they're seeking another route to this knowledge. Okay, so throughout these years, so sometimes I teach some classes on relativity and cosmology, but various other courses, various other teachers from different countries have participated and have taught courses, some of them specifically on relativity and black holes. And we cover the topics, of course, at conceptual level, but in some cases we do cover it in substantial mathematical detail. Of course, with the caveat that 12th grade students will know a significant amount of math. 10th grade students, not so much, but typically they are bright enough that they can catch up with the maths if there is a need. So the topics we cover in relativity are more or less the ones you can guess. So here's a list that I put together looking through the curricula of several years. So the ones that are in green are the ones where we go into some mathematical detail. Again, you can more or less guess what the topics are. I should mention that one of the things that we cover and that the students typically find interesting are some historical aspects. So for example, the period between Galileo and Newton, the development of physics at that time is quite interesting. Also the background to relativity, so all the experiments in the 19th century, trying to detect the ether and all of that. So these are mainly historical aspects, but typically we find that it's something that the students enjoy and it helps them understand how things appear, how paradigms shift in a way, and so on. So I think that's a very, I think it's a useful insight that we have. Just by way of illustration, here's some questions that the students get in the final exam. So relating to special relativity. So these are, so the exams are always written, as I said, it's a requirement of the University of Porto, so the students can get a diploma at the end. So here's some multiple choice questions on inertial frames, Michelson-Morley experiments, time dilation and length contraction, and the effects of relativity on GPS systems. Regarding relativity and general relativity and cosmology, again, the topics are more or less the ones you might guess. So we emphasize the difference between general relativity and the Einstein equivalence principle. We talk about the GPS as a practical application, also because we usually do geocaching at the camp, so we use GPS for doing geocaching. So it's useful that the students know actually how the GPS that they are using does work. We derive the Friedman and Ray-Chaudhuri equations rigorously in mathematical terms, although using the Newtonian approximations that I'm sure you all know about. And then we discuss simple Friedman, Match, Robertson, Walker universes, so single fluid, radiation, matter, cosmological constant. But often we push this a little bit further and discuss the transition between radiation and matter domination, or the onset of acceleration, so the transition between matter domination and acceleration, and so on. Again, here's a few more questions on the Einstein equivalence principle, gravitational redshift, the difference between the equivalence principle and general relativity, and also an example of one essay topic, so where the students are asked to write an essay and discuss a topic. So here, this is a sort of an interface between physics and philosophy, so the relation between physical reality and mathematical models that we use to describe it. So it's also a way for us to check how much the students have understood these concepts and how deep have they gone in their understanding. Okay, so what challenges do you have in doing this? So one big one is that there's huge difference between high school curricula in various different countries. So we had students from lots of European countries. We had students from Brazil. The curricula are very different, even sometimes in different regions in the same country where curriculum is organized locally. There's no national curriculum. So this is a challenge because we cannot a priori assume that the students will know the same things, or even students in the same grade in different countries will know the same things. So we have to, this is also another reason for the interviews. We can figure out how much the students know, what their starting point is, and then take it from there. There's also huge differences between public and private schools. So in Portugal, for example, private school students tend to have higher grades, but they actually know less than public school students. So private schools inflate grades in Portugal. We see that very clearly. Then there's the issue of mathematical background. So to give an example, 12th grade students will certainly know derivatives. They may or may not know integrals. 10th grade students, at least in Portugal, will not know derivatives. Again, this is not an issue. We can either one of the teachers or one of the camp monitors can sit down with the students for half an hour, explain them what derivatives look like, and give them operational rules how to calculate derivatives for polynomial, exponentials, logarithms, and so on. And typically the students can cope with it. Another issue is that there's actually misconceptions in school curriculum, even regarding Newtonian physics, that we have to fight. So for example, Portuguese high school physics curricula has several wrong things. Saying, for example, that the expansion of the universe is equivalent to the Doppler effect, which is obviously wrong. So students are taught this. They have to say this is so in the national exams, and then they get these wrong ideas, which we have to fight against. So this is something that we're now aware of, but it took us a while to learn where the students were coming from. So overall, our experience is that students can follow conceptual aspects quite well, even when they find some counterintuitive, just because it goes against what they learn in normal school. They might have sometimes difficulties with mathematics, especially the younger ones, but again, with some work and following them up during the 2 weeks, supporting them, that they can learn. And on the right, you see some example. Well, the course grades last year. So the grades the students got in the 2 courses, so in the written exams. These are in the Portuguese scale of 0 to 20. You need a 10 to pass. And the exams are not easy. I showed you some questions a couple of minutes ago. I would say the exams they're more conceptual than mathematical typically, but the level of difficulty is, let's say, at the level of a first year physics degree in university. So we do not necessarily give them an easy time, but they do very well in the exams. Okay, so in the last couple of minutes, just let me mention 2 or 3 quick things. So one community service project that we created is what we call the solar system trail. So in the first year, I gave the students the challenge to create a scale model of the solar system, accurate both in terms of sizes and distances. So initially we did this in a very rudimentary way. So here's our sun, 1.70 meters in diameter, and here's the Earth and Neptune on the same scale. So we made these wood boards, and then we put them at the appropriate distance. So here's 2 students measuring the distance between the sun and Mercury. It's about 68 meters on this scale. On this scale, Neptune is at the top of this mountain that you see in the background, so about 5.5 kilometers away as the crow flies. Again, we use the GPS to figure that out. So this was a rudimentary model. It's fun to do it, and you actually have to walk there and put the boards where they have to be. But of course, this is a very volatile version. So later on, we created a more robust version. We asked the Porto Planetarium designer to create some proper infographics, and now we have the solar system trail. As far as we know, there are 16 scale models of the solar system that are accurate in distances and sizes in Europe. We built one of them. And actually, this scale model of solar system is now included in natural sciences textbooks for 7th grade students in Portugal. So there's a whole generation of students in Portugal that will learn about the solar system, which students do in the 7th grade in Portugal, using this scale model as an example. So the people in Pedro tell us that they've had already lots of requests from 7th grade classes wanting to go there and do the hike, to do the solar system trail and learn about the planets. Last year, because of COVID, we had to have a hybrid camp. So students living in Portugal were at the camp in person, but foreign students had to participate remotely. And if you want later on, I can give you some lessons learned about organizing a hybrid event like that. So finally, I'm trying to take this a little bit further. If I had my druthers and I could change the Portuguese secondary school curriculum, here's 3 things that I would do, and these are things where I think Portugal is a little bit behind other European countries. So first, I think there's a lack of knowledge of scientific programming. So it's clear that foreign students know more about scientific programming than Portuguese students do. So for example, almost all foreign students know Python in high school, which Portuguese students don't. So I think it would be important to have scientific programming in the last 3 years of high school in Portugal, using Python or Octave or Julia or some other language. Then another bottleneck that we have is that in the 10th and 11th grade, physics and chemistry are not separate subjects. They're taught as a single subject, and typically in Portugal, this is taught by chemistry teachers. There's relatively few high school teachers with a training in physics. Most of them have a training in chemistry, and this is clearly a bottleneck. And then in Portugal, some national exams are in 12th grade, some are in 11th grade, and physics is one of them. So for example, you can go to physics or to engineering in university not having taken physics in 12th grade. So students typically prefer to take a different subject where it's easier to get a good grade and therefore boost your chances to enter university in that course, because we have a numerous clausus system. What are the bottlenecks to implementing this? Most science teachers in Portugal are in their 50s and 60s. They have very limited computer literacy. And this is clearly a problem, because even if the students want to do things like that or do extracurricular projects like that, students cannot support them. And we clearly have a teaching to the test approach in Portuguese schools. People are obsessed about school rankings and so on. And while that is the case, I think it's going to be very difficult to try and convince people to change it. Nevertheless, one can try. Okay, and with that, I will stop. And I'll be more than happy to take questions.
Thank you, Carlos, for your interesting description of your activity. Are there any questions? I have a question. How do you select your student? I read you made an interview. So what are the key things you are selecting for?
Right. Okay. So in the first stage, the students just send a motivation letter, a recommendation letter from a teacher. So we typically recommend a physics teacher and so on, and their school grades. So we ask for the grades as a sort of complementary thing. But as I said, our experience is that the grades don't tell you too much. Then in the interview, essentially, we want to check 2 or 3 different things. So one is emotional maturity, if you want. So the students are going to be 2 weeks isolated from their families with very little contact from the outside world. And sometimes that could be a problem. So we try to check that they are okay. Because sometimes you see that the student clearly has potential, but it's too young. So that sometimes happens with 10th grade students. And then we want to see, to some extent, what they know, but also how how persistent they are and how fast they can learn. So typically what I do, my strategy, if you want, is to ask them questions for which typically they will not know the answer.
Okay.
But then I give them some clues and see, first if they are persistent, because sometimes the student just gives up. And that typically is a bad sign, right? If the student cannot make an effort and try to get to the answer and pick up some clues, that typically is not a good sign. I try to know what they know and what they don't know, and I try to see how fast they can learn and so on. So clearly a 10th grade student will know a lot less than a 12th grade student. But again, if they can learn fast, if they are motivated, if they have the curiosity and so on, then
more their potential than their grades.
Yes, exactly. I mean, as I said, grades tell you very little. So even sometimes I have the experience of having two students from the same school, and even sometimes in the same class. So just because some teachers are very enthusiastic and they recommend the camp to the students, and then they get 2 or 3 students applying. And often I have students which you look at the grades and they're the same. You look at the recommendation letters for the teachers and they're the same, because typically the teacher doesn't want to do the selection himself or herself. So he just writes generic letters for the 2 students or 3 students. But then you talk to the students and you actually think these people are very different, right? So there, I think the interview is crucial, and eventually, it's the deciding factor. As I said, the Portuguese system goes from 0 to 20, and we had students with an average grade of 14 or 15 being selected, and students with a grade of 18.5 or 19 not being selected. So yeah, my experience is we ask for the grades also for the students to get the feeling that this is an academic program, it's not a 2-week holiday. But ultimately, I almost pay no attention to the grades. Maybe I pay attention in the first stage when I make the short list, because then of course I don't know the students, so I have to rely on all the information that I have. But ultimately, to assign the places, grades are almost entirely meaningless.
Okay, thank you. Thank you again, Carlos, for your talk. So we can go to our last speaker, Costantino.
Okay, I should be able to show to you something to speak, isn't it? Can you hear me?
Yes, perfectly.
I don't know from where to start, because I note many things this morning, and well, just for some criticism, I would mention the word exam that I heard from the last talk. So all these experiences are very nice, very peculiar, but they have to face the exam, which is even worse than Newtonian physics at the end of the course. Putting hands on is the best thing to do in physics, but is the last thing to be done in the school, in this school. I mean, in the school that we have to face on all the day. So this is a consideration that we can go back to. Sun grazing comets and general relativity is the last of the talks, but I want to start before because I don't want to forget. Okay. Work made together with Silvia Pietroni, and it's an idea of one of the possible experiences that we can do in a school. You can see some old printing of a big sun-grazing comet, and we can see some video from coronagraph number 3 and number 2. This is number 3. The orbits are very, very eccentric, and these bodies are the ones who arrive closer to the sun. There is something similar to what happened to the comet Schumacher-Levy number 9 in 1994, when it was disrupted by the tides of Jupiter and fall after on the planet. Equations, relativistic effect, and analytic formulae. Comparison with the planets, Mercury, Venus, Earth. They have precession anomaly, but this is very, very small with respect to the one of Mercury, which is even smaller than potentially the one experienced by the comets, the sun-grazing comets. So here there are some parameters in comparison between a typical Kreutz comet and the planet Mercury. A drawing, at this moment there is nothing better than that from our computations. What happens to the perihelion during the close approach to the sun? And the effect is even 40 times the one of Mercury. Words and numbers will be available on the proceedings, and so I don't remain on this. And I want to show, for example, this, which is a relativistic orbit around a Kerr black hole, which is the symbol of ICRA and of ICRANet as well, of Pescara site. This is the artistic realization, which is awarded during the Marcel Grossman meeting. And finally, I wanted to show the video of the comets directly from the internet, because it's the movie theater from the probe. That should go now. We connected to this facility right the day 18 of January, and we could see two comets contemporarily falling into the sun. So this is an experience quite amazing, even for me, but for students indeed, because there is the taste of the discovery. It's like to put hands-on on astronomy, but in this case on potentially relativistic objects. There are days in which this not happens. For example, today, I have seen some big coronal mass ejections in the last 9 days, but we don't see apparently any comets. But the frequency of these comets is kind of 1 each week, so it is possible to see very easily. All this noise is made by cosmic rays and from solar wind. So this talk is and it won't to be only an idea. The next 4 talks also are ideas, but let me ask if there are, oh, we can move the question at the end, let's see. The second talk deals in many ways with a very ancient instrument that is the meridian line. I gave a general title to include all the other 4 contributions, but we will see where the contributions are in this. This slide I have written during this session because Einstein first, and I said, well, back to Ptolemy. I was born too late for Ptolemy and too early for Einstein in the school. Ptolemy is ruled out as the old stuff, wrong stuff, and so on. But EP cycles explain everything. And in modern physics, don't say me that it is not an EP cycle physics. 6 parameters, like in lambda cold dark matter universe yesterday, the day before yesterday, I don't know anymore the notion of days with Australasia connection at 6 in the morning and end of the meeting in the late evening. But this model, dark matter, dark energy, resonance in particle physics, and so on, are ways to go back to Ptolemy. In which sense? Well, this is the orbit of the sun, and then, relatively speaking, the orbit of the Earth. Ptolemy says that the orbit is a circle, but it doesn't say that the Earth is in the center. There is an eccentricity, which is this vector, the distance between the center of the circle and the actual position of the Earth. This cross encompasses the 4 seasons. I wrote the season in the Italian style because in Australia they are in the contrary. If you know how to measure the transition between winter and fall, or between, fall and winter, winter and spring, and so on, you can put the data on this circle, finding the center of this cross and finding graphically the eccentricity. The result is astonishing because the eccentricity of the Earth in this way is exactly twice the eccentricity in the Keplerian orbit. So meridians that can be in the Church of Santa Maria degli Angeli, in the Square of St. Peter, so very big instrument, on the seal of my house, something very simple, can measure with a good precision these quantities. So let's start with the Santa Maria degli Angeli meridian line. I convinced the geometers of my institute to do a calibration of this meridian line, 50 meters long, illuminated by a pinhole, which is 20 meters tall. The line starts here and goes up to the end, to the Capricorn, to the winter solstice, or Capricorn solstice, 50 meters apart. The idea is to know very well each position of this meridian line with an accuracy of 1 millimeter, because the image of the sun is possible to be located on it with the same accuracy. This is the image of the sun for 300 years ago, on the 20th of August 1702, when the Pope Clement XI, the one who paid when he was still cardinal, visited the church. The image of the sun is as big as this. And the position of the image of the limb, the northern limb and the southern limb, is measured with a meter, and when the sun is on the floor, with a pencil to sign the position of the sun. So this is the experiment. You need a pencil, you need a notice, you write the measurement after you have the passage of the sun. There are other kind of experiment which can be done even out of the meridian line. For example, here we see the sun approaching the meridian line, which is behind the photo. During the last equinox that we can visit with the school, because afterwards everything was included in the lockdown. This is an experiment we made of meridian to measure the diameter of the sun in this way, using also a screen to obtain a better contrast of the image with respect to the background. This is the table with all the reference points taken with the total station by geometers. The work behind this number is a very, very complicated one. And this is the verification of the transits of the sun. Each point is an observational day. And we say that this meridian line is deviated from the true north of a very small quantity of about 5 arc minutes. This is a systematic geometrical deviation of this meridian line. Now we will see what this systematic deviation implies. These are other systematic deviations with respect to the line. There are a further small local deviation which arrives up to 5 millimeters at the maximum. Near the summer solstice, there is the Cancer constellation like that. This is the representation of Johannes Bayer maps of the sun, of this constellation 1603. This is the sun approaching the meridian, and this is the ancient solstice meter for 1702. This is the image of last day, 7th of July. So on 21st of June, the sun was nearly here. And on this line, I had all these points measured. They fit with a very nice parabola with the minimum 23 minutes from the ephemeris of Paris. So a very, very good result. Probably not completely determined, because during the data analysis, it is clear that if the data are not symmetrical, the result is much more complicated. So the idea is to have symmetrical data and as precise as possible. Otherwise, this delta time can fluctuate rather much around the expected value. But there is a tension, let's use another word in our plenary sessions about the H0 problem, the Hubble constant. There is a tension between the true solstice and the measured solstice with a parabola, because in the true solstice there is the contribution of the different orbital velocity of the Earth around the Sun, or vice versa. This is the publication of Bianchini on the wall, on the marble, for the 4 cardines of the year, solstice and equinoxes of 1703. This number have been translated into current universal time. This is the observation published on the book of Bianchini that are starting from 21st of June and are showing a perfect parabola but its peak is exactly 3 hours before the real solstice. This is the tension I was mentioning, even with perfect data. Another sketch from the book of Bianchini is this image representing the tool that Bianchini invented for measuring the position of the sun on its orbit, the transit of the sun, and following immediately or before the transit of a star. In this case was Sirius, observed in daytime. The distance in time between the two transits gave the coordinate of the sun. So what does it is referred to general relativity, in particular to special relativity. The stars are subjected, like the sun, to the aberration of light. And well, a step before, 2 steps before, here the time is given in local time, so after meridian, after midnight. When was midnight and meridian? In 1703, there were 3 moon eclipses. The moon eclipse is something that is independent on the time zone. It occurs in the same way in the whole hemisphere from where the moon is visible. This helps us to find the meridian transit because the eclipses of the moon were observed in the same local time. And now the famous equation of time has 2 components. The first component is the eccentricity 1, and the second one, and it's 0 during the aphelion and the perihelion. The second component is the obliquity 1, which is 0 at the solstice and at the equinoxes. This is the ensemble of the 2. So it was not easy, and even this splendid calculator is not synchronized with the real equation of time in 1703, but thanks to the 3 eclipses, we succeeded to do that. And this is the number translated into Greenwich Mean Time or Universal Time. After knowing that, we could know exactly the difference between the 4 cardines, equinoxes and solstice, compared with the ephemeris that Paris Institute of Mécanique Céleste and Calcul des Éphémérides publishes for all years, down to 15th century. And the result is summarized here. We have that the observations, the yellow ones, are not exactly corresponding to the times, would be 0, of the ephemeris of Paris. But if we include stellar aberration of the reference stars and the geometrical effect of the deviation of the 5 arc minutes, we find an agreement between the measurement of Bianchini with the effect, the special relativistic effect of stellar aberration. This is a snapshot from the book of Bianchini about the position of Sirius. He noted that the star changed during the seasons, and he considered this change, this is the tangent of the zenithal angle multiplied by 100,000. So the tangent would be 1.61. The angle is about 58 degrees. And this is the variation during the year 1702, 1703. Bianchini wrote that this variation was due to the temperature and to the meteorological conditions, but it was not like that. They were due to the aberration of the star. Again, the model of the aberration reproduces some way the data I have Bianchini plotted on his book, better than no model. Also, the equation of the motion of the sun projected on the floor is possible to be found. And through this equation, we demonstrated that 3 solar markers are connected with the same equation. So they celebrate King James III Stuart and his wife, Maria Clementina Sobieska, married in 1719, and the forms on the floor are 2 years later. So the one of the king and the one of the queen. And the hyperbola with the chi-square of this hyperbola. This discovery was already published in 2018, but this year we connected all the 3 forms on the floor, and this year we understood that they were all of 1721. Same work in St. Peter's Square with the obelisk. The obelisk is about 40 meters tall, so the accuracy of the measurement on the floor, provided that the contrast between shadow and light is found, is amazing. It is possible to find the motion of the sun around the meridian in only 10 minutes, the change of altitude. Other possibilities in Rome, we have the Clavius sundial at Collegio Romano, can be calibrated with by using the ephemeris, and it is an experience of a GPS of 5 centuries ago, because only knowing latitude and longitude, it is possible to understand this kind of calibration of these instruments. By the way, the Collegio Romano is the place, one of the birthplaces of stellar and solar astrophysics, thanks to Father Angelo Secchi in 19th century. This is the book of Clavius about his own sundial and in general to all gnomonics. And this is the moment in which I calibrated this sundial on April 2. Finally, in our school, Galileo Ferrari's Technical Institute, we have a soccer field which is shadowed by the gym hall of the nearby Lyceum, Morgagni, who actually was my Lyceum 40 years ago. The shadow of this Lyceum can be exploited to have a meridian line. This meridian line, I'm finishing, is drawn here, and minute by minute, we can sign the position of the shadow and seeing that the shadow moves at a given velocity, which changes slightly from the beginning to the end of the experiment, which lasts exactly
a couple of minutes.
Yes, which lasts exactly 1 hour. The typical time for a lecture. The students are outside, they are happy to be outside, but at the end of the year, they wonder, they are fascinated by the fact that the experiment lasts 1 whole year. This is the shadow, and this is the profile of the shadow. The hyperbole are compared, their opening aperture are compared, and the equinox is exactly in the middle. But you can do this experiment also on your seal. This is a book, this is a meter, this is a watch. And on the seal, I marked the shadow of the book put in vertical on the meridian line, knowing that the meridian transit time. From 4 data, almost casual, because I didn't imagine to present them and because I was in Santa Maria degli Angeli in St. Peter doing the other measurement. The result is 5 minutes of the ephemeris. You know, the error can be larger, but the result is astonishing. So finally, remotely, we did an astrocamp with the Observatory of Asiago leading institution, and I proposed all the students to do this experiment at home. The students are generally from nearby Venice, and the result of their shadow is very, very close to the average latitude of their observational point. This is the second day. The first day, their error were larger because it was the first time they did a measurement. But after they improved the technique and they learned it. So I have finished and I am ready to eventual question and answer.
Thank you, Costantino, for your presentation and excursus on the history of measurement. So, are there any questions? Costantino, what is the engagement of students? So are they interested in this very practical approach to subjects that are usually distant from daily life?
Shadows are not very distant for daily life, but they never saw that the shadows moves at different velocity. And even I always say, if you have to park the car, you have to know where the shadow will be. But this is, my doubt was, are you happy because you are outside? Or you are happy because you are understanding something? And they answer both. They answer both, and I said they were astonished that I went all the time there to measure. Not one time, all the time. Because this is the difference between school teacher and outside expert. We have to face 100 hours of lectures each year. And in 90 of that, they don't care of us. So I change my paradigm and I do 90 hours on the same thing until you understand. And at the end, I must quote some of the students. What is your favorite matter? He said, well, I find myself bad in all the things, but probably physics is the best. So Italian not, informatics not, that is their own special choice. All the things, physics is the best. I know that I don't do anything of physics. I immerse them into physics. They will understand from somewhere, someone else, what is physics probably. But they are immersed and they use their brain and their hands in a given problem. So that's my experience, and the statistics starts to be robust because 1,000 students for 10 years
Yeah, of course.
say the same. So I don't want to say, but if they say I am the best, it's not because I am only, you know, gentle or so, something like that.
Oh, no. I think that it's the power of hands-on activities that is very useful to get interest from students, because they learn that they can do things and not only learn from books and from the teacher.
I brought them in the church in the St. Peter Square, each class 6 times per year. It's too much. The colleagues kill me because they are not in the class, you know, they are not in the class to see and to do the homeworks and things like that. But when they say, let's go to the theater, okay, if we go also there, we go to the theater.
Different way of learning. Okay.
How far is the school to, let's say, the church or the theater?
Well, in Rome, a whole day goes. The meeting point is there, and we stay there, and that's it. You cannot go. In principle, in St. Peter, you can go in 1 hour, but you know, 1 hour go, 1 hour back by foot. The day is gone.
Yes.
Yeah. Do you have any maybe a written script of the process that you took in this whole process, or?
I have more than that. I have videos. The
Videos.
process is something that every time is different. It's something theoretical. Videos. We are learning every day new things from the stones.
I mean, I want to visit Italy now.
You are very welcome.
I think one of the teachers that I'm working with would really be inspired by this approach that you've taken in Rome. Yeah.
I am not the only one. I must say that there is another teacher that sends always the students there. So I know that she is the responsible.
Okay. Thank you again, Costantino. And so this is the end of our beautiful, interesting session. So I hope you have enjoyed it. And so I hope that next meeting will be in Rome, so we can visit these beautiful sites Costantino told about us. And so David, if you want to conclude your this session.
Only to thank you for organizing it so well, Matteo. Thank you very much.
Thank you for participating. And as I told yesterday, this recording will be available, I don't know, perhaps next week on the website of the conference. So yeah, keep in touch. Thank you. Thank you. Bye.
Thank you. Bye. Thank you, Matteo.
Bye.
Bye.
Bye.